when we design our SoCs, we're really designing something that are a balance of those particular constraints to meet an SoC, to build an SoC that will run those algorithms extremely efficiently. So I think that's a signature of our architecture, essentially algorithm first and then building a very balanced product.
On this episode of Embedded Insiders, Bob Kunz, Chief Architect at Ambarella, joins the podcast to discuss the company's current role in the low-power, high-performance edge AI market. We dive into the demands for AI compute and power generation for AI system designers and developers, and the architectural innovations emerging today. Next, Rich and Vin sit down with Jason Hallstrom, the chairman of the Embedded World Technical Conference, to discuss the upcoming Embedded World North America taking place on September 22nd through the 24th in Anaheim, California. Hello, everyone, and welcome back to the Embedded Insiders podcast. I am Assistant Managing Editor Tiara Oliver, and this week I am taking on the intro solo as Ken is away for travel. But I just wanted to hop on here and briefly tell you about some great upcoming events. The first is a virtual event hosted by Embedded Computing Design called AI at the Edge Day on September 3rd. The event focuses on navigating reliability and resiliency, and we've got some great sponsors and speakers, so be sure to check the description of this podcast to register. An upcoming interview in this podcast features Rich, Vin, and the chairman of the Embedded World Technical Conference. They're talking about Embedded World North America on September 22nd through the 24th in Anaheim, California, at the Anaheim Convention Center. Be sure to check the description of this podcast for more information about that event as well. As always, be sure to keep up with all of our content on embeddedcomputing.com and our YouTube, where some of our interviews are posted in video format. Be sure to like, subscribe, comment, and always let us know your thoughts, and we hope to hear from you soon. Now, here's Bob Kunz of Ambarella. Awesome. Well, hello, Bob, and welcome to the Embedded Insiders podcast. Before I get into some of our questions for today, do you mind giving us an overview of your role at Ambarella?
Sure. My role, I'm Bob Kunz. I'm the chief architect at Ambarella. I have been with the company for the last 22 years almost, from our early foundings, where we were involved in video processing and image compression. And I started after I finished my PhDs from Stanford in computer architecture, and then I grew up in the organization and now kind of oversee all of the design of our SoCs, especially the IP that we develop ourselves, which focus on AI. We have AI coprocessors, which are very topical these days, of course, as well as an image processing pipeline and video compression units. So I've kind of helped put the whole SoC together and coordinate between the VLSI design teams and the software teams to ensure that our SoCs will be able to meet its design requirements and make our customers happy.
Awesome. That sounds great. So I'm a bit familiar with Ambarella. I know that the company has been known for its work in low power and high performance edge AI. In your opinion, what makes Ambarella's architectural approach, different from more traditional data-centric AI companies?
Sure. I think a lot of Ambarella, we oftentimes say what we say is we have an algorithm first approach. Mm-hmm. And what that means is essentially we're designing, custom SoCs that are designed to execute a specific task extremely well. It started with video compression with H.264 in our early days, but it continues to our AI development now. Essentially, what we're looking for is what are those critical use cases where are the bottlenecks or inefficiencies in those use cases using sort of existing more general type of solutions, GPUs, CPUs, all of those have a lot of innate kind of flexibility. That's great. But if you have a specific task or a specific family of tasks, what are the kind of core algorithms and how much kind of reuse are those in those algorithms? And then designing some custom hardware that should be lower power, higher performance, be able to differentiate itself for those particular use cases. So that in order to really understand where the efficiencies and opportunities are for designing what is essentially is a boutique piece of hardware, we have to understand those algorithms, and we spend a lot of time studying them, and that's, I think, is the core part of our architecture. I think the nice thing about our architecture when we're finished is we are looking at many constraints when you're designing an SoC, right? You have a particular power budget, you have a specific DRAM budget, you have a price point that you want to hit. There's specific computational requirements that you need to make. When we design our SoCs, we're really designing something that are a balance of those particular constraints to meet an SoC, to build an SoC that will run those algorithms extremely efficiently. So I think that's a signature of our architecture, essentially algorithm first and then building a very balanced product.
Awesome. And speaking of some of those constraints that you mentioned, between AI compute and power generation, I know there's been a lot of talk about, if the supply can't keep up, the demand must adapt. In your opinion, what does that look like for AI system designers and developers today?
I think the interesting thing about AI algorithms right now is that at the moment they're fairly like simple. I mean, of course there's a bunch of different AI algorithms out there and different scales, but they're all based on the transformer-based architecture that's our if you actually look at the core common math behind it, it's fairly, simple. You have a compute phase that really requires as many multipliers as possible, and then the sort of decode autoregressive phase that requires as much DRAM bandwidth as possible. And those two phases don't really run at the same time, and the particular mix of those two phases will kind of depend on, again, whatever your algorithms and whatever your use cases. So in that respect, it's kind of an open book. I mean, all of these different companies are looking at the same hand, looking at the same kind of fundamental constraints and trying to decide where they're going to go. So I think when you look at the servers and cloud server based systems, they're really just scaling up. Hey, look, get as much power, put as many multiplier. Let's use HBM memory. It doesn't really matter. Cost isn't really an issue because we're going to make money on these individual services, and that'll justify the cost and the sort of expense. And I think that overall is great. I mean, in the sense that the server market and is able to achieve on a tremendous amount on these like frontier models and so on, tremendous power. But all of that can't scale forever. I mean, you're kind of looking at the power that these systems, cloud-based systems are consuming as a percentage of, the total kind of U.S. energy budget. It's starting to become a larger and larger piece of that total pie. It's a situation that can't scale forever. And so I think under that dynamic, there's going to be a couple things that will change. In the future, algorithms will change in the sense that, fundamentally, DRAM is such a bottleneck and compute is such a bottleneck, and it's so obvious that likely there will be over a 5 or 10 year period algorithm changes that will try to address those type of bottlenecks from the actual algorithms themselves. But from an SoC company like Ambarella, we can't really wait for those algorithms to change. I mean, we have to be aware of where things are going, but we have to build SoCs that people are going to design today. And I think one of the theses is that all that cloud computing is great. That will always be there. But there is this sort of space where edge computing will be very important. And in edge scales, you can't consume that much power, right? You can't fit in as much of the compute into such a small scale. So what I think that means is that you're going to find smaller networks, ones that don't require as much compute, as much DRAM bandwidth, and build some systems that will be the right balance point for those type of markets. So that's how I see the overall environment, is that the increase in demand, as you say, as the supply can't keep up, that really presents an opportunity for Edge to really come and find some really critical use cases that will be interesting, and where SoCs can find some business opportunity.
Awesome. How would you say constraints like power delivery and cooling and even thermodynamics will affect system architecture decisions?
Well, of course, all of those things are really important. I think the problem is that as you try to scale up with the amount of power that you need to deliver to one of these SoCs, then all the infrastructure around it has to scale with that. It used to be back in the day, like you needed cryogenically cooling your mainframes in order to be able to run them, right? You can burn a lot of power, but then you have to build a whole infrastructure around it that's very expensive. If you look at an application like robotics, like say humanoid robotics as an example, in those kind of form factors, you can build a prototype around some kind of robot. You can say, oh, hey, look, I use some off-the-shelf kind of GPU. It's got a huge heat sink on top of it. And we can demonstrate that this robot can kind of like run around and accomplish some great thing. That's good, but that's just a demo. If you really are going to productize that, if you're going to build something at scale, then you can't have a robot running around with big heat sinks everywhere. And in fact, especially in robot applications as an example, you're going to need to have a lot of that power for just the mechanics of actually running your robot. You don't want to have your compute, the brains of your system consume that much power, and to run the cooling system, to run the power demand, to run those type of cooling decisions. So I think that that really forces this kind of like low power space where you don't have to invest as much in all of that infrastructure. We had a demo a couple of years ago as an example, where we brought in a bring up board with one of our chips on top of it. And we told the customers, all right, hey, look, you can touch it. Yeah, no heat sink, no nothing. Just, oh, here, just, touch it. And for running the same kind of use case, the use case is a little bit different because the story is about 5 years old, but they could touch it. Now it was hot, but they weren't burned or anything like that. There was a perfectly fine kind of demo. So, those are the kind of products that Ambarella build. We're kind of really in that space of kind of low power. And I think you're going to see more and more of that, where you bring that sort of AI computation with some dedicated network to the edge. And that will force a lot of those systems, because those production systems won't really be able to afford all of that overall infrastructure. So if you can't rely on power, if power is constrained, if you can't rely on infinite memory bandwidth because that's constrained, that's really going to force kind of different architecture decisions. And I mean, I think it's a really interesting problem. The constraints in and of themselves are not that interesting. They're just inputs to the system. Well, okay, and here's the space that I'm operating on. But once you actually find that balance, once you find something where, hey, look, you can accomplish, this is the maximum amount of performance with the lowest sort of power. Those are the type of chips that I feel really excited building. It's and I think that also is successful in the market if in these production systems.
Mm-hmm. I mean, speaking of architectural decisions, in your opinion, picking your brain a little bit here, would you say companies are currently redesigning systems around efficiency, or are many still trying to scale through brute force?
Yeah, I mean, I think that brute force is certainly what we have seen, because all these algorithms, you can scale that up. As I said, the basic algorithm itself is fairly simple. It's just replicating how many layers and how many parameters, and then you have some minor algorithm tweaks that will sort of boost that kind of further. And So that I think is the traditional sort of approach that we've experienced. You certainly do see companies, I think, looking at that and saying, well, okay, how can we work around these constraints and build some other form factors? You see that with companies that are looking at like novel DRAM architectures, different packaging kind of techniques, different ways or our ways of compressing data when they go, to and from the memory system. So I think that it's sort of obvious that those companies are doing some of that. Certainly we are doing that ourselves. One of the interesting thing about in my role as chief architect is I'm really looking at things 3 or 4 years down the road. The products that we're actually out there selling on our roadmap are ones that I worked on a couple of years ago, and we could take just the nature of the SoC design taking so long. Mm-hmm. So I certainly am looking for much more efficient solutions. My whole story here is about edge computing, where power is really critical, efficiency is really critical, balance is really critical. And I think obviously other companies are kind of looking at that as well. I think one of the strengths of building an SoC is because you have control over the real underlying hardware. You have a lot of flexibility in how to design that particular type of hardware. It takes a lot of money in order to build these SoCs. And once you consider the amount of investment in terms of like tape out fees and using the latest process and so on, that you're talking about hundreds of millions of dollars. We're talking about building movies at that point in time. That's a huge amount of investment. And so a lot of times I think companies may look at this from an algorithm perspective, but you really need to have execution at the VLSI design level in order to be able to accomplish that. So certainly I think they're looking at overall system architectures as a way to do that. I think like the SoC as part of an overall sort of system. I think the advantage that, or the interesting thing that I think about is now you can actually control the SoC. It's a main part of building that and have some flexibility to change it.
Are there any architectural innovations emerging today that are designed to reduce data movement and improve system efficiency, or anything maybe that Ambarella is working on as far as this area?
Well, the DRAM bottleneck is, as I said, is like an open hand. A lot of companies are looking at different ways to approach that situation, both from a standpoint of better DRAM technology, but in that circumstance, you're sort of bound by physics in the sense that it's so much more expensive to move data, and we have physical limitations over packages that we can build. And so you end up hitting those constraints fairly hard. So then once you've actually maximized what you can do with physics, then the sort of situation is that what can you do with compression, right? Once we have this data, maybe just brute force sending all the data without just uncompressed across DRAM interfaces is not the right choice. Maybe we just use that data flow that we have more efficiently. There's different standards that are out there, ways of representing data that some consortiums like OpenMX or the MX data formats that companies are kind of collectively working together to come up with standards for data compression. But there's also other innovations looking at more complicated compression algorithms that are looking to use that either compression the KV cache or in some ways, which are key part of the AI processing, or looking at sparsifying the activation, the attention process. There's a lot of algorithm and infrastructure changes to kind of just reduce the amount of information that we need to transfer as much as possible. And I really see that from a standpoint of the architecture as the critical kind of component of it. I mean, compute itself, there are innovations in compute, of course. We are looking at that as well in the sense that it isn't all data transfer. Some part of the SoC is compute, and depending on what use cases you want to look at, that ratio between compute and data transfer are There's different mixes, and so you may make different choices at that point in time. But the interesting thing about compute is that compute, from a standpoint of power, is so much smaller than the actual data transfer, both off chip and then inside an SoC. Even transferring data across kind of a rectal limited SoC, your light is takes a long time to get data across that chip at that scale and at those speeds. So any kind of data transfer is going to be very expensive. So when it comes to like scaling compute, well, that's easier to do. There are some challenges there, which we spend a time looking at. I probably can't talk about, but I think that those are really the architecture situations. They're looking at algorithmic ways of compressing the data to take, which is very important because, of course, physics we can't really scale the sort of hard DRAM infrastructure that much.
So looking ahead, and getting your opinion, how do you see Edge AI evolving within, the next couple years, maybe the next decade? And how will edge architectures look over that time?
Yeah, I mean, I do think that edge kind of computing, as I've talked about, earlier, is going to become sort of a larger and larger component of it, because you have a lot of use cases for this AI algorithms, which don't involve going to the cloud. If you can make some local perception decisions, then if you need low latency applications where you need to make a decision very quickly, you don't have time to process a bunch of tokens locally, send it out to some cloud to be able to process and get some, answer back. That process of always checking in is, for some use cases, it's just really not that practical. Again, especially in sort of real-time applications where you have to process like very, very quickly. Those are very interesting sort of situations. And I think the cloud has captured those parts of the business that don't involve those edge cases. But I think over time, it'll naturally flow out to those edge use cases, and you'll see more support from the hardware community, the software community, to address those particular type of use cases as they arise. I do believe that, every 5 or 10 years, there's some massive algorithm shift, right? So 10 years ago, CNNs are really hot, and CNNs are going to solve all of our problems. And it's very good for image processing, honestly. Like CNNs, convolutional neural networks do very well with visual type of information because of the sort of spatial nature of images and pixels. And it's not really this sort of text that is sort of very sequential and logical. One thing sort of happens after the other. And then when LLMs took off, well, okay, now LLMs are the new hot thing. LLMs can solve all your problems. Well, I don't know what the next LLM is going to be, but it's inevitable some other algorithm will come along that will solve some problem that LLMs can't. And then that will be some critical use case, and then architectures and software systems and SoCs will have to adapt to that sort of new environment. I do think that overall, what you see, especially in these sort of situations where the bottlenecks are so obvious, is that you will have more kind of control, more tricks. People come up with more ways of optimizing that data flow. We talked about compression as an example. There's simple things you can do for compression. There's more complicated things that you can do to exploit every last little bit that you can out of SoCs. So I think like going forward, there'll probably more control in your inner loop. Maybe things will get smaller, but at this point in time, I'm just speculating about where the algorithms will go based on trends that I've seen before. The best way to predict it is probably what will be next is something that is significantly different from what we have now. So that's the interesting. If I had an exact idea of what to design, I wouldn't be able to tell you because I'd be designing something completely new for that next wave. But I'm not that prophetic, so.
No,
I
thank you.
think that,
That's right.
yeah. And so actually that to that extent, because you can't predict the future, one of the things that I think is really important for the SoC design is to build flexibility into your SoC. So, CPUs generally have lots of flexibility. You can run any kind of like software program. GPUs can run these LLMs and matrix multiplies very effectively. But any kind of flexibility that you can design into the system is something that provides you sort of a broader base of applications that you can run. But flexibility always comes at a cost. And I think the interesting thing is about SoCs, especially in these edge, is the right level of flexibility. What kind of flexibility that you can build so that it can be adaptable to the next wave of AI algorithms that come across. And I think we saw that when we went from CNNs to LLMs, is we built the right level of flexibility into our architecture so that when LLMs took off, we could very easily take sort of the existing infrastructure that we have and kind of adapt it to the LLMs and be able to demonstrate some performance right off the bat. And hitting that right balance of flexibility is really critical and easy to get wrong. And the problem is if you build too much flexibility into it, you can end up with a system that costs more than it needs. If you never use that flexibility, then you're just burning money. So I think that what people can do today to sort of think about SoCs for the future is really focus on what are things that are likely to change and sort of build enough flexibility into the system that you can adapt to it and make some bets, right? Make some bets about where we think we're going to go. And I think sometimes those will pay off.
Awesome. Very well said. Well, Bob, those are all the questions I have for you today. But as always, I like to ask if there's anything I might have missed or anything else you'd like to add.
No, I mean, I think we covered most of it. I think that's also why I talked a little bit about that flexibility. I think it's an important part because, hey, a beautiful architecture is a beautiful balance of all of these things. When you see a machine that is running perfectly, like any kind of you see like a car, on the road that is beautifully balanced and executes very well and can turn and can do all these things. It's a really beautiful thing to kind of look at. Often when you're taking in an SoC, it is much more difficult because it's not something you visually see. You just see it sort of in practice in terms of benchmarks and performance numbers. But when you see an SoC that is perfectly balanced, it's a beautiful piece of machinery and piece of engineering. And I think that's what I find really exciting about working in this sort of space is looking at those balance. And flexibility is really one of those parts of your design that you have to get right. I think one of the tricks that we have, and I think I'm sure other SoC companies have, is that you have this sort of flexibility. One of the tricks so that you don't have to add too much flexibility to a single SoC is you build flexibility across an entire family. One of the things that we can do is we have an engineering team that can execute very, very effectively, efficiently, I think, relative to peers. And so what that means is we've designed whole suites or families of chips that have the same basic type of structure, the same software interface, the same underlying kind of hardware, but scaled up or scaled down to meet different markets because Ambarella addresses sort of a very wide range of different markets, from very physical AI systems to much larger, kind of more complicated, edge AI systems that approach the complexity of some of these more powerful machines. But flexibility across the family is part of that story. Is you can say, look, I've developed my algorithms for your chip, but now I can do that. I can transfer that to some other chip, and you'll get the right level of balance. You'll see a nice machine, a nice balance point in both of those chips. I think that's I think one of the strengths of the architecture. And part of what I find really enjoyable is we're not just designing a single SoC. We're designing many SoCs, a family of SoCs that are able to solve a broad range of problems.
Now, here's Jason Hallstrom of the Embedded World Technical Conference.
Good afternoon and welcome to another episode of Dev Talk with Rich and Vin, where we talk about embedded stuff and we have a little fun. I'm Rich Nass, and the guy down there who thinks he's better looking than the rest of us is Vin D'Agostino. How you doing, Vin?
I didn't say the rest of us.
Oh,
Just
me.
Just you. Yeah, exactly. Hey, Rich, how's it going?
It's going great. Thank you very much. So interesting topic that we have here today. Normally we sort of segue into our guest, but I'm going to spill the beans right now. And our guest will be in a few minutes, Jason Hallstrom, who serves two roles at FAU. He's the executive director of the Institute of Smarter Cities, Space and Health. But for our purposes today, he's the conference chair for Embedded World North America. And what we wanted to talk to Jason about was some of the things that are happening with respect to artificial intelligence and how that leads into embedded system design. And I'm sort of on record as saying that we're not pushing hard enough on embedded. It seems like AI is really aimed at the consumer with medical stuff and the data center, and we're getting a little lost on embedded. So that was one of the reasons I wanted to bring Jason in to talk about if he agrees with that and what we're going to do to change that. But something you said, which really struck me, is that Embedded World North America, which is taking place late September in Anaheim. So we're like, was it 90 days out, I guess, something like that.
Yeah, 90 days out.
What we're talking about here and today with respect to AI might be different in 90 days because it's changing so fast. So if you're the conference chair, how the heck do you put together a conference not knowing where AI is going to be in 90 days? So I'll ask you first, Vin, before I ask Jason to comment. Is that true? Well, you said it, so I would assume that you agree with it.
Well, so, like everything else, life is a spectrum, and everything that we have today was built on yesterday.
Hold on. Life is a spectrum. What does that mean?
Well, it's not, I mean, there isn't one thing in time that stays static forever, right? So things are continuously changing, but they're built on the history that got us here today, right? So if you are gearing things in your conference or in a classroom or whatever towards someone understanding how to use AI, they need to know something about how we got here anyway, and the history isn't changing. So that part is going to be relatively stable. How it's
right,
viewed
but
today.
Our design community doesn't give a crap all about history. They need to know how to do their jobs.
Well, no, they better know a little bit about history because otherwise they think it's magic, right? If you think about AI in general, it's not 100% true, but almost by definition, AI is about sensor fusion, or let's say information fusion, right? Because AI is about using algorithms to predict something you can't measure directly. If you can measure it directly, measure it and move on. So you are either looking for something hidden in a signal, that's an individual signal, or you're looking at 2 or 3 different signals and using the combined information to predict something that you can't measure directly. And if you don't understand,
this is where I disagree with you. It's about making a decision on something that's going to happen in the future. It isn't just about making a static measurement and moving on. It's taking that information and predicting what will happen down the road.
I'm still stuck on you disagreeing with me. You can take an alternate view, but it's really an uphill climb. Yes, some of it's about the future, like if you're doing predictive maintenance, but something is about the, it's the church of what's happening now. As Flip Wilson used to say, for anyone who's old enough to remember Flip Wilson.
All 3 of our listeners who are old enough to know Flip Wilson, but go ahead.
Yes. I think there are things that you can measure like right now, like you can say, is a belt tension wrong? Is a belt fraying? Is is an impeller on a fan
I can,
out of balance.
I understand that, but it's about what do you do about that? What is the action that you take based on what you just learned about that belt?
Well, I mean, sometimes the action is to just stop, and that's no different than a thermostat saying, I'm now at temperature, so I'm going to stop.
That's not artificial. Just telling it to stop is not AI.
It could be if it saves a life or saves a bearing on a motor failing that's going to cost you thousands of dollars to fix, right? You have a fan blade that got hit by a piece of hail, and suddenly you notice by looking at the currents in the three phases of the motor that the motor system is out of balance. You can say, all right, I'll let them know, and I'll just let it run forever, and now they have to replace a bearing in 3 weeks instead. Or you can let them know that here's a problem and we're going to stop unless you tell me to keep going because it's 107 degrees out and you need your air conditioning, in which case it's worth the $1,000 or $2,000 to replace the bearing on your outdoor unit of your air conditioning. I mean, it could certainly be about the future. Like, you could decide that you're going to change the speed of something, or you're going to whatever. But it could also be, here's a condition that's happening right now, and I see it in the signature of the current that I'm looking at. Or, so in embedded, there's really three major areas for AI. You're either doing vision, right? Or you're doing audio voice analysis. Maybe you're looking for a screech to say that a bell is loose, or you're looking for a baby to be crying, or you're taking a voice command, or you are processing streaming data from an individual sensor or a group of sensors and looking at the combination of those outputs, right? Those are the three major areas of it. So, why are you talking to me? We actually have a guest.
I was just going to say it's time to, well, actually, before I bring Jason, I was going to tell you that I actually agree with you on your 3-step process. But anyway, let's ask Jason. How you doing, Jason?
Hey guys, doing great. Thanks for inviting me to the conversation today.
My pleasure. So you've been listening to all this, and my idea about that 90 days is pretty far out. What dawned on me, and we'll have to have you back for a second podcast, because as a professor, you got to go way more than 90 days out when you're preparing your curriculum. But we won't talk about that here and now. But hold on to that. Are you in agreement with what we're saying? Disagreement? And I know we talked about a lot of things, but why don't we start with the 90 days out part? Are you able to put into perspective what people need to know, or what they will know 90 days from now?
Yeah, Rich, I think that's a really good question. I think it's a really good point. In the words of the immortal Ferris Bueller, life moves pretty fast, right? So the stuff is changing very, very quickly. It's difficult for everyone to keep up with it. I think, in many ways, to sort of come to your point about the difference between organizing a conference and then being a professor, the timescales are quite different. In a lot of ways, organizing the conference is easier because we're asking the community, about 6 months in advance, what do you want to talk about? So what do you want to talk about? What's of interest? But I will say it's really hard to predict what the community is interested in talking about and what the community is interested in hearing about. So, if we go back in time, and you and I, Rich, we talked about this before when we started talking about 9 months ago, what we thought the major themes of Embedded World would be about. We had embedded intelligence as one of 5 themes. That was the original plan. And when you look at what does the community want to talk about and what do they want to learn about, well, it's embedded intelligence all over the place. So, I think in many ways for Embedded World and conferences in general, you have to listen to what the community wants to talk about. It's awfully hard to predict in this space what it is they're going to want to talk about. And in this case, folks want to talk about AI, and they want to talk about AI up and down the embedded stack in ways that I think we hadn't anticipated.
So let's talk about that a little bit, because my comment was that embedded is someone getting the short straw when it comes to AI, because so much attention is being put on the data center, and at the other extreme on the consumer side. And I said medical before, and I'll say it again, the advances in medical AI are huge. And embedded seems to, it just has always moved slowly. Are you seeing that people are making the same advances in the embedded spaces that they are at the other two ends of the spectrum?
Yeah, I mean, I think you're right. I think it does take longer for these kind of advancements to make their way into the embedded space. And I think that's just the classical problem of resource constraints, right? So what we can do in the cloud, sort of to borrow concepts I've heard elsewhere, what we're going to be able to do with computers that live on our desk or live in the cloud, it's always going to be more than what we can do with the device we carry in our pocket, no matter how powerful that device in our pocket might be. So it does take longer for the things that emerge in data centers to make their way down into the embedded space. But with that said, I think we've seen a real shift from last year's program. So last year, when we looked at where was the AI activity in embedded, it was really all about the edge. And I would say it was fairly siloed, right? So it was about how do you get AI models to run at the edge, and what we meant last year by edge was the base station or the gateway. So not really
tell
down
the
into
audience you're doing air quotes.
Oh, I'm doing air quotes for edge. Yeah, for edge and gateway. When we look at where is AI making its way into the embedded space now, for one thing, I think what it means to be edge has changed. So I think now it's much more this, it's fog, right? So folks are interested in AI at the data center. They're interested in how do you integrate AI at the historical edge, which was the gateway or the base station. But now we're seeing a lot of interesting work where folks are moving AI all the way down to the most resource constrained devices in the embedded stack, down to those individual sensors, which is why I really like Vin's example of this kind of fan blade scenario where you have a fan blade that gets struck with, whatever, a piece of debris, and then you start to see bearing failure and trying to figure out how to do some predictive maintenance, right? When are you going to see a failure in that bearing? That's actually an application that we've begun to see. So folks doing on very resource constrained 16-bit micros, doing AI for predictive maintenance. I mean, that's something that we weren't thinking about, 4 or 5 years ago. So I think we're really starting to see, I think this is sort of the point where we're going to see AI moving up and down the embedded stack. And by the way, that's not even to bring up how AI is impacting the development cycle, which is a totally different thing, right? So the application of generative AI to firmware development, to PCB design and schematics and silicon design and blah, 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 right? On and on and on. So it's kind of really, I think we're seeing a watershed moment for the embedded community.
Do you make a distinction between AI and machine learning? Because the example that you guys are talking about is a machine learning example, in my opinion. And it's not as advanced and doesn't need the processing that you do to do real full-blown AI. Jason, and I'll let you answer too, then.
Yeah, Rich, I think of machine learning as AI, and I'm going to borrow a very old definition of how I think of AI. So historically, when we talked about what was artificial intelligence, it was the discipline that would eat itself. So the idea was that AI is using a computer to do something that computers could not classically do, that only humans could do. And then it was AI. I think, when we look at what's happened over the last 3 to 4 years, when folks talk about artificial intelligence, the vast majority of the world is talking about generative AI. They're talking about LLMs. So, I still think of AI as being that umbrella term for, I find it hard to describe actually. So as being the umbrella term for all things related to perception, prediction, and generation that are not discrete, right? Or not deterministic rather, which are stochastic.
Ben?
I completely agree with that, right? I've always looked at it as when you think about intelligence in humans, it's not about the amount of knowledge.
Is that a joke?
No. Some intelligence,
He was using air quotes. I saw him.
I'm not. I mean, if we talk about artificial intelligence, the other side of that is real intelligence. And where does that come from? Does it come from beavers building dams, or does it come from the way humans are interacting with the world around them? Right. So, when we talk about intelligence, the uninitiated might consider talking about knowledge, but it's really about synthesis, which means you are taking a bunch of things that you know and synthesizing something new from it, right? And so I think of artificial intelligence in the same way. When you look at let's just take streaming data analysis, because that's a very illustrative viewpoint. You may not know what it is that's going to help you predict something. So you're going to take 120 lines of data and you're going to look at it the same way we used to do reduction of digital circuits with looking and seeing what's a don't care. Like, what doesn't matter? The output doesn't matter whether it's a 0 or a 1. And you're going to do the same thing with this. You're going to say, okay, in the conditions that I've created that I want to be able to detect, of the 125 lines of data I'm taking, only these 3 actually matter. And so now you've done reduction and you say, if I just look at these 3 quantities, I don't need 120 sensors. I need 3 sensors, or I might need 2 sensors and look at the data from one sensor in 2 different ways. And from that, I can predict that something is going to happen. So it's synthesizing a reality that it's not measuring directly. And so that could be done on a very simple 16, or I mean, there are a lot of 16-bit parts out there, but if you're running ARM, you're at 32, right? And everybody at this point has got an ARM part. So and it doesn't matter whether it's a small M0 plus kind of device or whether it's an A9 architecture mixed with 2 other cores or something, right? So, I mean, there's a big, wide gamut of things you can run this stuff on, depending on the amount of computing power you need. And in many cases, you don't even need some specialized hardware to run, certain AI algorithms. A lot of this stuff can run using the DSP extensions on the regular ARM instruction set. So, this is something that's really, for me, about synthesis. And so you can say machine learning is an AI. Okay, all I would say that all AI is not machine learning, but all machine learning is AI, right? It's a subset of what's going on.
Yeah,
Okay.
I agree.
Before I move on to the next subject, I want to swing this back to Embedded World. With all the stuff that we just talked about, in what way will this be covered at Embedded World, Jason?
Rich, if I have the numbers right in my mind, I think we have 86 technical talks at Embedded World this year. At least 60% of those talks touch upon AI in one way or another. And that's everything, just as we're talking about. So that's everything from perception to prediction, machine learning on very resource constrained 16-bit micros to higher end. I think it's always funny when we talk about embedded systems now, and we talk about something like a DGX Spark, which will be represented at Embedded World. That's an embedded device. It is technically resource constrained, but it has 128 gigs of RAM. So the constraints are quite different than they were, just a couple of years ago. We're going to see AI in the development cycle, everything from generating test cases to, just as I said before, generating silicon to managing the overall production workflow. We're going to see nice talks on how do you when you have these AI modules that are integrated within your product and the product is deployed and those AI models need to be tuned and modified over time, how do you guarantee reliability? How do you manage trust with users? I mean, there are a lot of interesting questions there. So you're going to see all that represented at Embedded World in at least 60% of the talks.
Excellent. When I think of Embedded World, and historically, it's always been about the ecosystem and all the different pieces of an embedded system all coming together, or the pieces of the design of an embedded system all coming together. In what way will this be represented at Embedded World?
Yeah, I think that's a great point, Rich. And I think, the flavor of Embedded World to me remains the same. That Embedded World has always been about bringing that full ecosystem together. I think in many ways AI just amplifies that. So when you think about what it means to build not just an AI system, but an AI product, that brings in everything from what are the chips that are needed to implement that product? What are the accelerators that are right for that particular perception or prediction task. How do you manage the models? Are these going to be edge first models, or are they going to be models that we're going to draw from the cloud and we're going to compress and prune to try to squeeze onto the device? We're going to see this represented in the overall workflow. So we're going to see not only on the exhibit floor, we're going to see vendors who have new production pipelines that are all AI first pipelines for deploying and managing firmware and managing the whole life cycle. So we're going to see this up and down. I mean, really up and down the embedded stack, everything from chips to firmware to connectivity to cloud. And then, of course, everything that lives in the middle. So you're talking then about safety, security, compliance, trust, and so on. So I think AI forces the embedded ecosystem to really come together in ways that we've seen before, but I think are accelerated by the need to deploy these incredibly complex systems that still in some ways I have these black box components, right, that are very, very tricky to reason about and to ensure reliability of.
Let me spin this back to you, Vin. What are the places in embedded design that people have a tough time with, where they should be looking to an event like an embedded world to get more help, whether it's in the classroom or from the vendors on the exhibit floor?
Well, so you're not going to like my answer.
Do
Because
I
it's
ever?
not, that's how this podcast got started, right? Well, that and the rival schools, but we won't get into that right now. So,
Well, now we got a third school in the mix.
I know we have a third
How
school
much
in there.
engineering can they learn in Florida, right?
Oh, they can learn some really good engineering.
Wait, now I got to know, what are the schools? What are the other two schools?
I went to Stevens Institute. He went to New Jersey Institute of Technology. So,
Oh, all right. All right.
so we,
Hardcore
we
New Jersey.
Hardcore.
well,
Jersey.
yeah.
All right. I'm an
Well,
Ohio State guy, so there you go.
I was a Connecticut boy down in New Jersey. So
Anyway.
anyway, so the thing that I see I hate to say in my practice, in working with customers, the thing I find the most challenging, or that they find the most challenging, is figuring out how to apply it in a meaningful way, right? It's like you and I have talked about this before. This is not news, right? You and I, Rich, are old enough to remember when radios were and TVs were labeled as solid state, because transistors were a new thing and everybody wanted to advertise that they were using transistors instead of tubes. And then it was when, MPUs and NPUs started happening, people were making things that were smart. And then when IoT started happening, people were making things that were connected. So there's this marketing aspect to the technology that honestly, we as technologists, we may poo-poo it, but it's those kinds of things that have made these things become ubiquitous enough that they have continued to evolve to the point where they're interesting to us and can be used in many places, right? Just think about something as simple as a C compiler. Nobody cared really about C compilers being that optimized. I mean, there was some optimization, but it wasn't until they had to be used. It had to be used to write code for really resource constrained devices, where the compilers and optimizers got so good that if you know what you're doing, you couldn't possibly write, I should say, you wouldn't write assembly code as small or as fast as compiled code, because even if you saw the parallelism, you wouldn't write it that way because it would be unmaintainable. Whereas the C compiler, you can write code, and that didn't happen because something was running on a DEC 10, right? It happened because it was running on 4K of code space and 512 bytes of SRAM. So the application of this, because people wanted to make something smart, is what made the ecosystem around it evolve. And so now we're seeing the same thing with AI, and everybody wants to say they have an AI element to their product, whether it's a graphic design package or whether it's a remote control on the TV or your thermostat, right? So, but people do struggle with, how do I add this cost to my product and create enough customer value that the customer is willing to pay more for the product that has AI in it or has the technology in it, right? This is the core of the business that I run, which is responsibly and appropriately adding technology to a product to increase customer value. And
That's the first time
honestly,
we've ever done a plug for your business on
well,
our
because you interrupted me, because now that we have a professor here, I'd like to say that we don't teach this enough in schools. We are so excited about teaching the technology and the pinnacle, and how to make something happen, that why to make something happen seems to get lost in the sauce, right? And so I think that that's an important part of creating engineers. And as we look at, and you and I have talked about this, we look at AI on the enterprise side, which Jason brought up, right? There's multiple places where AI touches a business. More and more early engineering relevance goes away because you can use it to do the menial tasks that new college graduates might be doing on the way in. So what do we teach them in school to make them relevant and significant in the workforce? And it's about how to do this well and create value with it, not just do it because you can.
Okay, I think you got a little off topic there, but I certainly get where you're going. So
Well, no,
back
it's
to,
all, I mean, yeah, but it's all about the AI ecosystem, right?
Yep.
In the end.
Well, Vin, I think it's a really interesting perspective, and I agree with you. I mean, I think what we're seeing with the use of this word "smart," right, is the same kind of thing, just as you said, with the word "connected" that we saw now maybe 6 or 8 years ago, something like that. I think my favorite example, and Vin, neither you nor I would benefit from this product, but they have a connected hairbrush, and so this connected hairbrush measures the quality of your hair, and it communicates it to an app, and so on and so on and so on. And they have another one, of course, everybody has seen this, the connected toaster and the connected toaster oven, all these things. These strike me as totally insane. I don't see how those create any value for a customer. Maybe I'm biased on the hairbrush, but I guess that's maybe a different story. And I think we're seeing that same kind of thing again, right? I think engineers, maybe by our nature, right, most of us got into it because we're excited to create. We're excited by the technology, right? I mean, we're excited by AI modules, we're excited by connectivity, we're excited by all this stuff, even before we understand how it's going to be productized or what value it's going to create for the customer. So I think maybe on your point on training, I think that sort of comes back to the business side, sort of rounding these students out, right? I think if you have folks who are only trained on engineering the technology and look at these amazing technologies that we can produce, then I think all they think about is, how do I shoehorn this AI module into this product, or how do I shoehorn this connected thing into a toothbrush, or whatever. So I think it's important for engineers to have some of that product side experience, either to develop that on the job, or to have that as part of their formal training, and have some business education to understand, how do you figure out what the customer really wants, what creates value for the customer, what improves the overall experience. And I think sometimes engineers make it out of these programs and they don't have that background, and then it just becomes, how do I integrate this awesome new widget into the product?
Yeah. By the way, I have an IoT toothbrush.
Come on, man. What are you
I
doing
have an
today?
IoT toothbrush with gamification, and my wife makes fun of me all the time. And now, of course, that I've said this, Rich will as well. And I will tell you that my dentist has told me that my teeth are cleaner. And and I've won that, you win badges on the app, and it shows you coverage of your teeth and how long you're brushing, and it pushes things to the cloud and gives you histograms of usage and times of day and all kinds of ridiculous things that I don't look at very often, but it's there. And I will tell you that, you have to be someone who's into gamification to some extent, right? Like, I'll show her, look, I'm at 100%, and she doesn't really care. But my dentist has said, whatever you're doing, keep doing it, because there's much less on your teeth when we're doing our, triannual, not semi-annual, 3 times a year cleaning, right? So And so there are ways where you can apply the technology and have it make a difference, right? I will spend another $230 on a toothbrush when I need to replace this one because I really like the idea that I know that I'm doing a good job.
All right.
So,
this is probably a good place to end. With respect to Embedded World, Jason, when, where, and how do people get more information?
Yeah, so thanks very much again for the conversation today. So Embedded World North America is coming up. It's right around the corner. This is in September. This is going to be in 76 days. So it's right around the corner. For more information, please visit embedded-world-na.com.
And it's in Anaheim, right?
And this is in Anaheim, California this year, September 21st to the 24th.
Very good. That was Jason Holstrom. He is the conference chair for Embedded World North America. I am Rich Nass, and the guy with the shiny smile down there is Vin D'Agostino. Have a great day, guys.
Thanks, guys.
Thanks, guys.
Thanks, Jason.
Thanks for listening to this edition of Embedded Insiders. For more daily news, videos, and podcasts, visit our website at embeddedcomputing.com.